So we are going to in this class we are going to have some brief discussion, some a sort of brief introduction to how we define head joints in terms of linear transformation. As you are aware of the fact that in linear transformation, if there are spaces and there are, we can construct a dual space, and there is a particular relationship of isomorphic mapping to each element of a space vis-a-vis its dual space, so that there is some functionality attached to it, to the point to the to two members of those dual set. So in this context, we have to say let V be any vector space and let Y be any element of V prime. So for any linear transformation, for any linear transformation, A on B we consider the expression so for each fixed y, the one function of y prime, which is defined by y prime is defined as y prime x is defined as axy is linear functional on V. So using so we are coming back to our bracket formalism. So the way we, if you remember, we defined previously also bilinear functionals. How the linearity property was extended to how we define the bilinear functions in case of these finite dimensional vector spaces, and the bracket formalism, the sort of identities how we compassed them. So that was handy. So in the same way, here also we take recourse to that sort of bracket formalism, where we use a sort of square bracket notation for y prime as well as for y. So if there is an element in space and there is an element in dual space, so we define ax y as x y prime. Now what's the thing? So we allow y to vary over v prime or the dual space. Then the procedure makes us to correspond y to y prime. So this is the procedure. There is an element here and there is an element here. So how we can, if there is a linear space and linear transformation, then element linear transformation, and it's that element in that dual space. So, and of course you can write y prime is equal to e prime y. So you can write it this transformation if you write it in terms of square brackets. So So you can write it. So if you change, so you can write it. You should write it like this. It should. So linear transformation will allow an element in this space and this space. This relationship in the dual space should hold in terms of that bracket formalism. And further, if we are going to assert further, if we are going to assert here, if we are going to assert a prime is a linear, a prime is linear transformation on V prime, and if y is equal to alpha y1, alpha 1 y1 plus alpha 2 y2. So what will these sort of this bracket, how the form they should take? So they will take this form if you say it, if you see. So y we will write in terms of y1 and y2. These alpha 1 and alpha 2 are the scalars which associated with these vectors y1 and y2. And y is defined in terms of y1 and y2. So if we translate them in terms of this bracket formalism, so it will take the form of x of a prime y should be equivalent to ax of y. So I have written first this, then this. So I reversed it. So it will be equivalent to alpha 1 ax times y plus alpha 2 ay times x. Sorry. Oh, this is ax1 times y. This will be, sorry, so if it's between y1 and y2, it's ax times y1 alpha is a times, so ax times y2. Now it's fine. So y is in terms of y1 and y2. So alpha 1 is here, ax y1 and ax is y2. So you can write it like this also. This bracket form you can check it out whether it is like that or not. It's sort of as a committed. You can write it, or further you can write it like this: alpha 1 times x a prime y1 plus alpha 2 times x a prime y2. Now it's x. So we have the scalar. Initially, a scalar was associated with x. Now the scalar is associated with the y, but in terms of a prime. So now further you can write it further. So these are different ways we can write this commutator. In this case, we have written x. This is this thing. So we have doing y1 and y2. So in the same way, the scalar is now associated with this y1 and y2. So you can take this form. So again, you can now in the third case, if we allow the alpha 1 and alpha 2, these scalars not outside the brackets, we just allow them to be inside the brackets. Then further, we can write it as alpha a prime y1 plus alpha 2 a prime y2. So these are the different ways. If there's a transformation, linear transformation in space, and how we can relate that linear transformation in some dual space. And if the elements of those linear transformations are further decomposed into some elements, how will that those in terms of bracket formalism, there can be different forms. We can write the same relation in that linear transformation. Now further, if you just see that linear transformation as a prime. So you had a, now it's A prime in some dual space, you can further write it as further A prime linear transformation A prime. So you can have linear transformation as A and dual transform as A prime, or vice versa. If you take a linear transformation A prime, but here it's also called the adjoint. Now comes the our how we define adjoint. Adjoint or dual of A. So now there are some interesting properties of this dual of A or adjoint of A, which may be interesting or which are very much useful in further understanding of linear transformation. So to begin with, the algebraic rules which are very much there. For example, 0 is 0, adjoint of this is 0. So adjoint of 1 is 1. The way we multiply in scalar vector spaces, multiplication with identity element will give the element back. It will not matter. So in the same way, adjoint of this will be back, and the same way, so adjoint of this will be adjoint individually, or the multiplication of scalar will be outside, so it will not the scalar will not anyway have any influence on this adjoint. It will come out unscaled as a prefix to that adjoint. In the same way, AB prime. So now if you change the order, so it will not also matter. Or if you have inverse of adjoint, so it will one is you have inverse of adjoint. The other is you have adjoint of the inverse. So that's it. These are two different things. The inverse of adjoint and adjoint of inverse, they are the two are the same thing. So it doesn't matter. And further, so these are set of properties 1, 2, 3, 4, 5, 6, 7, 6 and 7 property. 1, 2, 3, 4, 5. This is 3, 2, these are 2, 3, sorry. So 2, 3, 4, 5, 6, 7, 6. The first property is the maybe so the numbering in the book is like this. So now what 7 can be interpreted like this. So maybe this adjoint of inverse and inverse of adjoint, if they are same. So what does it mean? So all of these proofs are elementary. You can do it in one like one or two lines, 3 lines. So it's trivial in that sense. Sign that, for example. But for 6 and 7, this and this, it might need some amount of effort. For example, if you have abx of y, you can write it as bx of a of y, a prime y, or as x of b prime, a prime, and y. So you can write it like this. So in the same way, A inverse, for example, A inverse A is equal to A inverse A is equal to 1. So that's fine. So applying 3 and 6, applying 3 and 6, 3 and 6, if you apply it here, uh, so we will have A inverse prime A prime is equal to A prime A inverse prime is equal to 1. So this implies that A prime is invertible and equation. This is valid. So in the same way, there is something called A double prime is equal to A. So you should not, so in a sense, sometimes this A double prime or A double prime is A. So even though it doesn't look that as if it's adjoint of A prime, no, it's a linear transformation of A adjoint of linear transformation of A prime in some dual space, which will give this A back. So it's not adjoint of A double prime, it's adjoint of A prime can be defined as, so it's adjoint of A prime rather than adjoint of A. So adjoint of A prime or this A double prime will give the element back. So it's slightly, you have to think over it. Now, so again, if you want to extrapolate it vis-a-vis this identity, we can write it as Ax of y is equal to x times A prime of y is equal to A double prime of y into x. So again, so A double prime of this is A back, this is y. So these are different ways of writing. So here we have written adjoint of A prime is A. Adjoint of A prime is A. So this is another way of importing this property here. So if you remember, we had previously also used something, a space called a reflection. So we have an operation and you just have a reflection, you invert it back, it will not matter in that sense. So if A goes to, if A, this is a, if A goes to, if there is a reflexive finite dimensional case, then the mapping A goes to A prime is 1 to 1, or it's also sort of algebraic isomorphism. So the need of algebra in that sense that it's somehow connecting the elements of space, linear transformation in one space with that of a dual space. So algebra can be in that context. Sorry. Sorry, in the sense he has not used word, so I may be wrong, he has used word anti-algebraic isomorphism. From the set of linear transformation into set of linear, so if there is a linear transformation V into a linear transformation V prime, so it's this word anti is customary, it's not the way I thought it. It's customary in the sense that it's somehow attached because of commutation rule 6. Commutation rule 6. Commutation rule 6. Commutation rule 6. That's fine. Again, so if we have one theorem is that so there is a theorem It's not only adjoints, now adjoints of projections. So one important case is that multiplication doesn't get warranty, which means AB prime is not necessarily equivalent to A prime B prime. If you remember the linear transform, the linearity property, we said that it may or may not be commutative in its details. If you work out a particular differential of a function, if there is a differential of a function which is inside a which is operating in a linear transformation, it's not always true that the commutation relationship hold. So the cases where they hold, they are there, but in the linearity transformations, the commutative may not always hold, or the product of two elements, one of them it may be zero, divisor may be zero. So it's not, if the two elements are non-zero, their product may be zero. That's also the case. So that's a non-triviality. So in that context, so this relationship, so from this, if the commutativity does not always hold, so if we define this thing and there is an adjoint defined vis-a-vis this, so multiplication doesn't get turned around. So multiplication here doesn't turn around. Now the theorem is, so as a theorem, if E is a projection, so if E is a projection on N along this N, then E prime is a projection on this M star along N star. Oh, yes. I'll just write it like this, N star. And this is N. So the proof of it is, in that simple sense, so we know that E prime square, so projection of this projection is back, and if we define some space composed of two spaces M and N, so this product can be defined as N0 cross of N0. So it's not only useful to find subspaces consisting of solutions such that E prime y is equal to 0 and EY is equal to y. So there are two cases. In one case, the product of this is 0 scale, and in other case it's y. So I can take it as an identity element. So what if E is mine? Now, first case, if y is in M dual space, then for all x prime E prime y is E of x with y. So these are properties I'm going to enumerate. So if E prime y is equal to 0, then for all x in M, we can write x times y is, so again, so I'm going to use these properties here. So we can write it as ex of y and x times e prime of y is equal to 0. So in the same way, we can have third property as well as fourth. I'll write fourth property. So e of prime is y, then x of y is equal to x of e prime y, and now you can just e of x. One second. Huh? Then ex y is equal to 0. Let's stop here. Okay, let's stop.